Alright, second to last proof, proof 9 about projection matrices. Um, so there's a bunch of stuff that we have to go about proving. I'm going to list it out. So M is a k-dimensional subspace of, I don't know why it's supremum, is of R of n, and A is a n by k matrix whose columns provide a basis for m. So, firstly, we got to prove that P is equal to A of t, A inverse of AT. Um, is you got to prove that this is the projection matrix, and the way we go about proving that is by doing the following things. First part is going to be for all m, so like the components of the m matrix, P of m is actually equal to Pm is equal to m. The second thing is for all W of Rn, W is M, lastly all W elements of Rn, W minus BW perpendicular to M. Alright. Part A is kind of easy to go about doing, so I'm wondering if you should copy them. I'm gonna probably not going to do that. So A, since the columns of A span M, which is kind of given by definition, then it would mean that for all M, there are elements of the matrix M, and there exists an X such that M is equal to AX. Then it must mean that P of M is equal to, we're just going to sort of use the projection matrix thing, A of A T of A inverse AP A X is equal to A I K of X, which is equal to A X, which is equal to M. Alright. So for part B, we got to prove for something in some vector in Rn, projection matrix, like if we apply the projection matrix to that vector of Rn, we actually do get the matrix, the resultant is something in the matrix M. The image is something in the matrix M. So for all W part of R n, start off by P W is equal to A T A inverse A T W is equal to A X. This is for some X. The last bit is actually some linear combinations of the columns of M, because we're essentially multiplying them, and since the columns of A span M, then it must mean that the product will be in M. This is more of an argument. Since this bit is always sort of columns of A, like I said, so it must be that they are in M, which would then mean that P of W is in M. All right. What about doing C? All right. So you're going to consider again any W vector which is in R of N, and we're going to let sort of P of W 0, which is a part of M. This we kind of are getting from the first part that we proved that everything, sorry, in part B, which is that if we multiply something, we do get something in the matrix M, in the span of matrix M. I don't know why I said image a while back, but anyway. So let V equal to W minus BW, which is equal to W minus M0. Alright, now we want to show that V is orthogonal to all M. To all M. So since A is comprised of all of these vectors, so what that means is that we kind of want to show that V is orthogonal to all the columns of A, or and if it is in fact orthogonal to all the columns of A, this would then mean that V is actually a part of the kernel of A of T. Alright, so that's kind of what we want to show. So that would then mean that A of T, V is equal to A of T W minus A T P W, which would then mean that A of T W minus we're gonna sort of use whatever, like the definition of the projection matrix thingy. So A T A inverse A T W is equal to A T W minus A T omega. Why did I say omega W? So it cancels out to give us the zero vector, the sort of zero vector. So that would then mean that this is in fact in the kernel of AT. So V is in fact an element in the kernel of AT, which then means that V is in fact perpendicular to orthogonal to M. Thank you.